Yes.
Okay. Hi, everyone. Good afternoon. It's a pleasure to me introduce Professor Jose Raul Quintero. Professor Jose Raul Quintero is full professor at University of Del Valle in Cali. Professor Raul Quintero works in this specific equation, more precisely, study well-posedness, existence of solitons, stained waves, stability, and so on. He has several students, more than 10 students until now, a PhD and master, and received several awards. One of them is the member of the Columbia Academy of Exact Physics and Natural Science and Columbia Mathematics Society. It's a pleasure for us receive today Jose Raul Quintero. We'll talk about solitary wave solution for a order KKK type equation. Thank you, Raul. It's nice to see you here.
Okay, thanks a lot, Roberto, for the introduction, and thanks for the organizer of this meeting to let me talk about this particular problem. This is a joint work with Professor Liliana Esquivel from the University of Puerto Rico in Mayagüez. Okay, so let me show you the outline of the talk. Some comments on the model, some techniques that we use to solve this type of problems. A basic result for even positive kernels, which is the main core of the result. A special family of parameters, as I'm going to show you. There is a very important class of parameters that we have to deal with to be able to get a traveling wave solution, and the main result and some references. So regarding the comments on the model, this is called the KDV model, which is like a fifth order KDV equation plus some nonlinear terms. And so main difference here with the fifth order KDV is that we have the presence of this gamma ux squared, which make a huge difference from this model to the KDV. On the KDV model, in general, P is a polynomial, and those constants are, those parameters, mu, alpha, and gamma are constants. So, but somehow you have to determine the sign of this thing. So this model includes some other model like the KDV1, which is occurs when Pu is equal to rho u squared. The modified KDV, or the KDV, the KDV equation, which is exactly this one when P is a quadratic polynomial. So before I go further, I'm going to just mention that this model appears in a more general class of model by Peter Olber and Kichinamasi in this work, in this reference number 1. So this is the model. Our case corresponds to beta equals 0, right? And in this model, P is a cubic polynomial. Even this constant P here could be taking 0 because we can make a translation in the spatial variables to take care of this. So essentially, we have a QU squared plus gamma UQ. So I'm going to mention some comments about this work by Kichinamasi and Olber. So they look existent and non-existent criteria for having sec-squared type of solution for this problem. And the first thing, they have to deal with only cubic polynomials. When they plug this information in the model, P has to be cubic. And the coefficients, they were able to, to determine what type of coefficient can be used to take this type of solution. They find like 5 regions. 3 regions are relatively open subregions in which there are 3, 2, 1, and no such sec-squared solutions. So that means that, depending on the parameter, it's possible not to have solution or to have some of the solutions. And in the first and the second regions, most models have a solution for a unique or precisely 2 possible wave speeds. So they limited the wave speed too. So this is a challenging model. just looking for this type of solution. So that means that it doesn't mean that there are no more solutions. They could have more different solutions for sec-squared. So the analysis that they did showed that there is a relationship between the coefficient, right? And so you have these two equations, and our case corresponds to beta equals 0. So in that case, so these two equations reduces a lot, because from the second equation you have beta equals 0, you have the left side, the right side 0. So you want to have alpha different from 0, so R is 0. That means that R is the coefficient of the cubic, the square coefficient. So essentially, in this case, the only choice that they have in this region is, for this type of solution, is P to be only a quadratic polynomial. So this is just the analysis that they did. And then, I was looking for this result a lot, trying to see how if this was proven or not. But so I decided to go inside and try to prove the existence result. So there is a paper related with this KDV model, which is the Kawahara equation, which is the KDV of five order KDV. And then here, so they include this nonlinear term to force the model to be Hamiltonian. So that's why G has this special form. And then this model is very important now. This model has been studied a lot. There are many results. This model were derived in different contexts. And there is a derivation by Peter Olberg when G is of this form. G, in this case, G is homogeneous, and also Sufira, Hunter, Schroeder, and Craig and Groves, they also look for different type of nonlinearities. And in the last one, which is a Peter Olberg work, this is very special because this one is now homogeneous, right? This is for order 4, and this is order. So there is a term of order 4, and this is a term of order 3. So, so this type of equation of order 5 have been studied a lot, and then we want to try to say something about this KDV model. So one important fact is that in these models, 1 and 3, the general one, with gamma no 0, do not fit in the Hamiltonian structure, as happened for the KDV, for the AKDV, for the ABCD system, for the Kawahara model. I mean, there are many models with this Hamiltonian structure. And then in those cases, when we have the Hamiltonian structure, the equation can be written as ut equal to H prime of u. H is known as the Hamiltonian, and J is a skew symmetric operator in some Hilbert space. And then in this context, traveling waves are characterized as critical points of the action function, which is this one where Q is defined this way. So for this type of problem, so when you want to just show that you have a critical point, then there are two cases. Essentially, one is the concentration compactness principle by Lyons, and traveling waves correspond to minimizer of the energy functional. And then in this context, you just try to minimize the IU, which is like a norm, right, with this constraint KU equals 0. So essentially, you have a positive bounded function, and then you can take minimizers, and then trying to see you can get from this minimizing sequence to get a solution, a minimizer. And then so when you do that, and then you essentially you have a measure, right, associated with the I. So I is the integral of something which is quadratic, which is like a norm, and then you define a measure associated with this I, and then for any minimizing sequence you have a sequence of measures and then positive measures. So you have to use this result by Lyons to determine in what case you are, because there are two cases. One is vanishing, when all the mass is gone. The other is the dichotomy, when you have the measure splits into parts, and both of these has some mass. And the other one is the compactness, where all the mass is concentrated in some points, in a sequence of points. So now when you translate these points to the origin, then you have everything concentrated at zero. So you use this concentration at the origin, and then you use the key fact is to use a local embedding theorem to be able to prove that your minimizing sequence converges after a translation to a minimizer. And this is the end of the story. The other possible technique is to use the Montan-Pi theorem by Ambrosetti and Rabinovich in the late 80s. They developed a huge theory about this when the functional are palestra. And so we don't have this here, but we are able to use almost the same approach that they did in the palestra case. And then there you have to use the vanishing case. You have to use the local compactness, but also that you have a condition like a vanishing one. So in this case, you only get weak solutions for the problem. In the concentration compactness, you get strong solutions. And then those are the cases. And the other case is when you are able to write your solution like a kernel multiplied by the nonlinear part of the equation, in the case that the nonlinear part is positive. And here K is an even positive function with some properties of decay at a plus or minus infinity. And then in this case, in this setting, the problem is equivalent to find a fixed point of a nonlinear positive operator defined on a cone in a Fresnel space. So this is a theory developed by Karnowski for positive operators. And for example, this was used by Benjamin Bonavosset to address many problems, systems using this technique, right? And the problem with this model is that, with this approach, is that the basic cone to be used is this one, because we want to have traveling wave, right? So you want to have something like which is even and decays to zero and plus and minus infinity, and then this is the natural space to look at this problem. And but what's the main point in general, right? If you look at the Bonavosset or many problems, many papers, the nonlinear only contains powers of U, right? If this were a system, then you have components of U, and then you have here, you have component, then you have like a powers of the components, or product or the power of the components. So in those cases, so this is the natural space, right? So the huge problem now is when in this part, in the nonlinear part, appears a derivative, which is a huge problem, because then you have to include this in this cone, and then when you start putting derivatives here, then it's going to be a lot complicated. So in those cases, that theory doesn't apply at all. So you have to look for something else, and then the main point in this approach is that somehow you have to check that this operator is compact, and then in this cone, you are lucky because you have the Arcelor-Ascoli theorem to address this, and then so this, in those cases, this is the nice space. What happened with our model? So our model doesn't fit into the Hamiltonian structure, and secondly, the nonlinear part contains derivatives of U, so which is a huge problem. So the only choice that you have is just to go to the classical fixed point, which is the Picard method. The idea is to take initial data, construct a sequence using the recursive sequence, and then try to that this thing converges to something. What's the problem? The problem is simple. You could have a contraction, and you could have everything, but then you are able to prove that the sequence converges, and then but in this problem, zero is a solution. So in general, you prove that there is a solution, but it could be zero. Otherwise, you have to do something to avoid having zero as a solution for this problem. So this is the main idea that is involved in the discussion. So the strategy is simple. It's like combine this two methods, the Krasnodębski method with this. Is just to write the equation as a fixed point equation, to write the traveling wave equation as a fixed point. So once you have that, then when this BF is this kernel, but so in general, this kernel, if you are lucky, this kernel is positive, right? And then it decays to infinity, and not only decays, sometimes it's decreasing, is even, and then the second thing is use the Picard method. In other words, it just construct a sequence in the appropriate space with a special initial data, and then it just the sequence is constructed in this way. You have Bj, and then you can go to construct Bj plus 1, and then show this sequence is a Cauchy sequence in this space, and then trying to avoid having a zero solution, which is, and then you have to work a lot to be away from zero. So here is the core of this thing. So once you want to get a Cauchy sequence, you need this A to be like a contraction, right? To be able to assure that you have a Cauchy sequence. But now for this other side, to be far away from zero, and then you have to impose another condition. So here that's why it's very special to take in account the parameters of the model, because somehow the conditions will depend on the parameters. So it's not for any kind of parameter that you have existence of this, but for a special class. But in this talk, neither the paper, we didn't specify any special region, but I'm going to show you a condition that must be held to be able to do this, to construct this sequence and to be far away from zero. And then let me go to the traveling wave equation. So the traveling wave equation is this one, number 6. And then you just go put this type of solution there, and then you get this. And then you take the Fourier transform in both sides, right? And then you just you get the formula for the Fourier transform of B. And then we are lucky because this is K of C times the transform of the nonlinear part. But then sometimes we don't believe in God, but God exists. And then we write this equation this way. You can see that B is a convolution. This is exactly the ACV operator. So this is the fixed point operator. So what is KC? So in this case, KC, the formula, there is a book, Bateman manuscript, that has many formulas. This formula appears there. And then these numbers are real numbers, A and B, and they are computed in this way. So one thing is important is that mu squared plus 4 alpha C has to be positive for having A and B and real numbers. So the analysis that we are going to do here has two parts. One is the the simplest one, which is the quadratic polynomial, and the other one is the general one. The important thing is that the general case, follow essentially using the same ideas of the particular case, rho u squared. So, okay, now, as I mentioned to you, since we are dealing with a convolution issue, right? So there is a nice work by Benjamin Bonavose, right? That was used to show the existence of traveling waves using the Karnoshevsky positive theory. And then in this space, in the space of continuous functions. And then it's just a nice result, very simple. The proof is very nice, very simple. And then you define this kernel where k is an even positive function having a Fourier transform in L1, right? And then there are many nice properties that are transferred from k to bf, to this new function. And then if this function is even, and then bf is even, or if f is odd, the bf is odd, and is bounded, if the other is bounded, if it's positive, if bf is positive or negative. And this one, A, B, C, D, are in this paper by Benjamin Bonavose. And the part D is that f is positively decaying to 0 in plus or minus infinity, unbounded. And this is the proof was suggested by Professor Jerry Bona in a personal. Now, and I was able to prove that if f is a non-increasing function for x large, right, and then bf also has this property. So this is very important because we are in this. We put something in this class, we will stay in that class. So this is very important for the discussion here. Okay, so as I mentioned to you, okay, let me check the time. As I mentioned to you, we have to check a special family of parameters. We are going to check it only the case, the quadratic case. So let me define k as this number depending on the parameters, and n, which is this number that depends on the parameters. Remember that a and b depend on the parameters. And then a simple observation is this one. If we set minus alpha equals c equal to 1/3 mu, and then magically a and b don't depend on the parameters. And this number, mu squared plus 4 alpha c, which is very important because it has to be positive, is trivially positive. So this means, right, you take gamma less than rho, and then the k is 6/mu times rho. And rho m, pues you factor rho m, it's the same, rho m, and then you can see here is the core. So if mu is large enough, k minus rho m is negative. So k is less than m rho. And then this is a necessary condition for the next step. So you fix a positive function, right? You take with this kind of parameters, you take rho equal square root of mu large, and then look at the left side. So m doesn't depend on the parameters. Rho b0 is fixed, and rho can be taken large. So this can be bigger than 1, and then k in this case is 6/mu, and then this can be small. So this is the core of this. This is the core of this. And then with that, just try to use the Picard method for this. So you just construct the sequence, and then try to do the right estimates. Try to essentially to get the contraction argument. So the first thing is that this is bounded. The bj plus 1 in H2 is less or equal than k times bj to the power to the square, And then this follows just by multiplying and doing integration. You just go there, and then to bound this one, which is an integral in L2, and then you just go use the fact that ux and the ux is in H1 and b is in H2, and then you get this estimate. And then you get this bound, which is like the contraction argument. And then you get, but to get this one, you just get this is coming from the previous theorem, and then this is the left. Let me go to the next one. This here. So this is the left part. When you multiply the equation by this term, this is the left side. So you can bound this in this way, right? And then you just do the computation, and you finally get. I don't want to be too technical, but you get this one, which is that we claim. And then now, to be sure that the fixed point is not trivial, we have to be sure that that at zero at least, so the solution is far away from zero. So you just define this. This is the sequence, and then I'm going to show you that for any x in 0, 1, bx is greater than or equal to L0. So it's very simple because you state B1, right? B1 is this. And then now use that this is positive. And then you just take this one. And then use the definition of the minimum, the infimum. And then you get this. And then just estimate this integral. And this integral, right? This integral, you can show that this is bigger than this. And then you get this is the m, the number m that appears there. So you get that. So you get that at any x in for any x in 0, 1, you have the bjx is greater or equal than H0. So this prevents us to go to 0 when we get a Cauchy sequence. And then the next step is just to show that the sequence is a Cauchy sequence, which is essentially because we have a contraction. And then you just plug this in here and write this in this way. And then you use the condition that we proved there and use that this is a number less than 1. And then now, if this is less than 1, and then you have use the geometric series converges, and then you bound this. So you have a Cauchy sequence, right? And then we're in a Banach space, and there is a trivial. There is a limit in this space, and then it's not trivial because the value of 0 is far away from 0. And then we have this one. Now, if you take this function b naught to be even, and then the same result, the only thing that we add is that the solution is even. Now, this function b0 is 0 far away from is 0 outside of compact set. So that means that this function is decreasing far away from then it's decreasing in near infinity, so the solution also is decreasing. Sorry, decreasing in infinity. So essentially, this is the theorem. Now, in the general case, we can do the same, right? Try to do the same computation. I don't have too much time to do this. And then to obtain a similar result. Now, the same approach can be used. Instead of having gamma ux squared here, just put a key and a q, a polynomial, right? P and q, which are a non-negative coefficient. So essentially, you get the same. So this is the essentially the talk. And thanks a lot for your attention.
Okay, thank you, Raul. Thank you very much for your nice talk. Some questions or comments, please. The audience can ask in the chat or open the microphone. If you have some problem, some questions, yes or no. I have a curiosity, how. Okay, you work in the case that you have KDV and Kawahara, right? High order 3 and 5, right?
Yeah. No, only 5. No, this
Only
is
5.
only 5. It doesn't work
Okay.
for other case.
Okay, so you believe that you can put the more general operator like -1, J plus 1, del X to J plus 1, for example, to recover KDV, Kawahara, and the others?
There is a condition needed there. So the coefficient of the first derivative can be 0. So it's impossible to because we are in this setting. So you put you forget about the fifth order. So you are putting 0 there. So we are not allowing to put 0 in those coefficients.
Okay.
Yeah. No, you cannot put 0 in any of these coefficients.
Okay, you prove some result of stability in that?
No. The problem with this is that this model doesn't have the Hamiltonian structure. So
Okay.
so probably we could try to do linear stability, trying to put B plus the traveling wave, and then linearize this, and then to see what happens. Yeah, but
Okay.
I haven't checked that. No.
Okay. More questions or comments, please? The audio is open as well, the video. Everyone can turn on the videos. If not, if you don't have any questions or comment, let's say thank you again to Raul. Thank you, Raul.
Okay, no, thanks to you for the invitation to this talk.
Thank you, Raul, this afternoon, Noemi.